9.4 sequences. You've been dealing with sequences for like a really long time, probably.
Just didn't know it.
A sequence is just a fancy word, basically. Actually, it's not even a fancy word. It is the word for an ordered progression of numbers. Some examples of this, like 5, 10, 15, 20, 25. Pattern, that's what I was thinking.
Pattern.
A sequence is just a pattern, basically. And so these actually kind of are different examples of how we can write these things. So like, you can just write it out. This is 5 things long. Or we've got this sequence, and then...
Anytime you see the ... and this stuff, that means keep going forever and ever.
Right, so this is saying we could keep going past 32, and then this is saying to find any term in our sequence, we could use this formula 2 to the k, and then even after that it would also keep going. This is saying that our sequence is 1 over k for values of k, 1, 2, 3,
right,
and so on.
And then we just keep going. I mean, the only person I know of that can count to infinity,
yeah,
Chuck Norris.
I've heard that before.
He
about
did it
him.
twice.
Wow, twice?
Yeah.
That's impressive.
I know, right?
And then this is going to be a common thing we'll see. There's little curly brackets around this, which we
fancy brackets,
which we know usually that means some kind of a sequence or set of numbers. And then we use these subscripts to talk about the term. So like this is our first term, our second term, our third term. It keeps going until we get to some kth term.
Yeah, which would be whatever term you're on.
Yeah, and then it could keep going after that. And sometimes we just abbreviate that type of sequence A with a subscript of K. And when we do that, we're talking about the whole sequence.
Not just part of it.
Yeah.
Right.
So vocabulary, we have a finite sequence, has a countable number of terms. Countable as in, like, you could count
number of fingers and toes.
Yeah. So that's like this first one. We can count. This has 5 terms, so it's a finite sequence. And on the other side of that is an infinite sequence, has infinitely many terms, so you couldn't sit there and count it. So
Chuck Norris could.
Yeah, only if you're Chuck Norris. And so these 3, because they have the ... which are ellipses.
You know what? I don't know what those are called.
Something like that.
Yeah, some fancy.
And it means they keep going forever, so they are called infinite sequences.
Mm-hmm.
So there's 2 different ways that our book talks about defining sequences. One of them is explicitly. And typically the word explicitly means like obvious.
Right. Like I want this term right here, right now.
Right.
Like I want this specific piece of information without doing any other work. I just want to know what this value is.
Right. So in this problem, this example, we have a sequence here. This is considered defined explicitly because no matter what term you want, you just plug in that number for k and it tells you what that term is. So it asks us for the first 6 terms. So if I want the first term, then I'm finding a of 1. That means the first term, and I plug in a 1 here.
Everywhere you see k, you put a 1 in.
Yeah.
Yeah.
And so 1 minus 1 is 0. So our first term is 0. Then,
six of those? Oh, you're going to write a bunch.
Maybe. We'll see what happens. So now I plug in 2. So 2 squared is 4. Minus 1 is 3.
That's 3.
So 3 squared minus 1 is...
8. It's 9 minus 1, it's 8.
Okay.
Well, I don't even know why you hesitated. I have never been wrong on this stuff. That's going to be 15, BT dubs.
Okay.
Go ahead, work it out. 16 minus 1.
Now there is a pattern that's happening here, I believe. Well, there has to be. It's a sequence, but like a pattern that we can actually know. Like we're adding 3 to get between here, adding 5 to get here, adding 7 to get here. I must need to add the next odd number, which is
25
9.
minus 1, which is 24. Everybody knows that.
Yeah, so it may or may not be worth it for you to spend your time trying to figure out the pattern.
36 minus 1 is 35.
Yeah. Okay, so this is...
Hey, look, there's a pattern.
There's a... Here are the first 6 terms.
They go up by increasing numbers of odds.
Increasing odd numbers, right. Each time you're adding
Shut
the next bigger odd number. So, but that would be really difficult for us to write out all the way to the 100th term.
Yeah,
so
who wants to do that?
It's really nice that they gave us this formula. So we put in A100, so that's 100 squared minus 1, which is 10,000 minus 1.
999,999.
No, wait, I have the decimal in the wrong spot. I don't know if you said it right or not, but 9999.
Well, I said something like that,
yeah.
So that's got to work, right?
Yeah, so all of these are our answers.
And it's explicit because if I want to know the 15,000th term,
whatever term you want,
just
you got
plug it in.
Explicitly. It's obvious, like explicitly. Example 2, the other way is to define recursively, and if you're in computer science, you may have heard this word before.
Maybe you have.
My husband, who's a computer science person, is not fond of this word, and I, as a math person, sometimes recursion is not fun.
No.
But this really isn't that bad for sequences, because what happens is they'll tell you like the first term or maybe even the first and second term.
They might get you started here.
Yeah, and then they tell you how to find all the rest of the terms using a term you already know.
Right, like I can't, like if you were to ask me to find the 100th term of this one,
That'd be super difficult.
I just couldn't do it because I would need to know 99 first, but then I would need 98.
But they do actually ask us for the 100th term, so we're going to have to figure out.
For the love of Pete!
So let's just start off, though, with the first six terms. And so basically recursion is plugging things in backwards.
Yeah.
Like using what you already know to get
find,
something new.
Yeah, use what you know to find what you're being asked.
Okay, so B1 equals 3.
You do that while I play 2048. So
okay, B2.
Let me know when you get there.
And if you plug in a 3 everywhere that
Hold
n
on,
is... You can play, just don't disturb us over here on the video. Okay, so n is 2, so we're saying b of 2 minus 1 plus 2. So that's really saying b of 1 plus 2, and we know that b of 1 is 3. So we're really doing 3 plus 2, and that's 5. That's our next term. Right. The cool thing about this is if you can wrap your head around it, what are we doing each time to get the next number?
Adding 2.
Adding 2 to the previous number. So b3 is simply 7. B4.
No, after. After B3, not before.
Is 9. B5 is 11.
What is that?
Your computer keeps like lagging on me.
Don't blame my computer
totally
for your issues.
Here's the first 6 terms, and so as Mr. Hazelwood pointed out, we don't really want to sit here and do this until you get to the 100th term.
No, that's
There's got to be a better way.
There's got to be.
Let me just write out what we got here. 3, 5, 7.
I think I see an 9, explicit formula.
11, 13. We've got odd numbers starting with 3. So how could we write a formula for this? We want it to start with 3, but then we're adding 2 every single time.
2n.
So that's 2n.
Let's start with 2n and we can modify as needed.
Okay. So
check it. 2
So if
times,
I plug in 1,
right.
Do I get 3? No, I don't.
No, because that makes it 2 plus 3, which is 5.
Right.
So what if we go 2n plus 1?
And then put that in parentheses? You mean minus 1?
No. Just erase the 3 and put a plus 1 there, because we were 2 over. So
right, we're 2 over.
So what if I put a 2n plus 1? Now Mrs. Stevenson is thinking of a different pattern, and that's the beauty with these. There are
different ways of thinking of it. So if you say, hey, we're starting with 3 and then we've got 2n, and you try that for 1 and you got 5. So he's saying instead of having 3, let's subtract 2 and get 1. Well, that's going to give us what we want.
Yeah. Now, Mrs. Stevenson was thinking of something different, and that's perfect. That's why these problems are kind of fun.
Yeah, and also can be frustrating.
Yeah. So what were you thinking of, Mrs. Stevenson?
I was thinking of, like, basically what you would do is in parentheses you would do an n-1 situation. Because when you plug in 1 here, now I've got 0. 0 times 2 is 0. And
so look, both of those work. That's the cool thing.
Okay, so to get the 100th term, we need to plug in to one of these 2 formulas, 100.
A hundy.
A Hyundai?
No.
Like a car?
No, a hundy, like 100, like a cool way.
201.
Like if I got a hundy, I got $100. You know, a hundy.
201. Okay, and if I do it this way, if I do it this way, I have 100 minus 1 times 2 plus 3. That also
just
works
99.
out. 99 times 2 is 198 plus 3 is 201.
There you go. Chitty chitty bang bang.
Or if you want to, just keep adding until you get to the 100th term.
If you think you're as good as Chuck Norris, knock your
it.
socks off.
The definition time, limit of a sequence.
When limits are already kind of tricky anyway, so really pay attention to what's going on here.
So the idea here is we have some sequence of numbers, and we want to think about if we could approach infinity in that sequence, like the number of terms.
Whoa, only Chuck Norris can get to infinity.
Yeah, so sometimes it works out that a sequence is actually headed towards a particular number.
Right.
Which means the limit does exist, and it gives you some actual number, which we're calling L here, but you'd actually get like 5 or something.
It'll be like 27 or
yeah,
1/3 or something like that.
When that happens, we say that the sequence converges, and that L is the limit of the sequence. But otherwise, like if we can't end up getting to some number, because it either just keeps getting bigger, like bigger and bigger numbers, or smaller and smaller numbers towards negative infinity, maybe it oscillates.
Yeah, it goes back and forth, like 1, -1, 1, -1.
So those are cases where the limit's not going to exist, and we say the sequence diverges.
Right.
So on these 4 sequences, we're going to figure out if they converge or diverge, and if they converge, we're going to give the limit.
A converges.
Okay. How do I know?
I don't know.
Okay, well, let's look at it.
Okay.
I start with 1/1, which is just 1, 1/2, 1/3, 1/4. If I keep going, 1/5, 1/6, 1/7, 1/8. What's happening is I'm getting smaller and smaller numbers, right?
Yeah.
Because whenever I make the number on the bottom of a fraction bigger, it makes the actual number itself smaller. So what happens is if I try to plug infinity in here, which you can't really do,
That's
but
a big
conceptually...
I'm going to plug in 1/10 jillion billion.
Yeah, so, and your calculator won't do that, but you could actually take your calculator and do like 1 divided by 100. Yeah. And then do 1 divided by 1,000 and do bigger and bigger numbers. And you should notice that the bigger the number, the closer and closer we're getting to 0.
Right.
So that means that this sequence A does converge, like Hazelwood said, and its limit is 0.
Think of this as when we're looking at the limit of the graph. Are you eating right now? You are
just keep talking.
So what if we took the graph 1/x and we looked at the graph of 1/x and we looked at the limit of that as x goes to infinity? And what happens
like
on
in
that
behavior.
Like in behavior, and what happens on that is the graph of 1/x approaches 0. And since it approaches 0, even though it technically never touches 0, we go, you know what, this has a limit of 0. That's the same thing that's happening right now with the limits of the sequences. They're going to approach something, although they're never going to touch it. And we've seen this before with all the different graphs that we've investigated this year.
Right. So this next one, they didn't give us a handy formula. So this was A. I'm going to have to try hard to make sure that you can tell what's working
What's
where.
going on there?
Okay, so it says 2/1. So if we wanted to write an explicit rule for this, like the bottom we could call n, like the first term has a 1 on the bottom,
mm-hmm.
and on top it has n plus 1.
Right.
And then you can check and see if you look at the pattern, like the next term is the second term, so that's a 2 on bottom, 2 plus 1 is 3 on top, so that works. So if we think of this like in behavior, we're saying as we get bigger for n, as we go closer and closer to infinity, is this actually going to head closer and closer to a number?
We'll need to use L'Hopital's rule.
We're not in calculus, so we can't do that.
But that's really easy to tell us.
Okay, so we have to use the tools that we have right now, Mr. Hazelwood. We don't know calculus.
Partial fraction decomposition. We
That's
just did
wrong.
That. That's not wrong.
No, you can't use...
Why couldn't you?
Because there's only one thing.
So it'll be really easy.
So plug this into your calculator.
How about just
separate
out?
Behavior?
Look, it's going to be n/n plus 1/n. How hard is that?
That's not partial fraction.
That is too. I just separated it into 2 different fractions. That's a partial fraction decomposition. And n/n reduces to 1, so you have 1 plus 1/n. Now, that is partial fractions.
Okay.
It's just easy partial fractions, which makes it not seem like partial fractions. You got a chip on your arm. What the...
So what's the limit of this? Well, we just said that 1/n, this first sequence, would go towards 0. And so really we just have 1.
Just 1. And the limit of a constant is just that constant.
Yeah, so, and you can plug this into your calculator and graph it, and you're looking at the n behavior as we go to infinity. Or you can just plug in bigger and bigger numbers for n
and see what you get.
Mm-hmm.
But they should start getting closer and closer to 1.
Yes.
Yeah.
Okay, next sequence. 2, 4, 6, 8.
Who do we appreciate?
Hazelwood.
Yay! All right.
So this should be pretty easy to see that this converged, by the way. because we got a number.
It's not in green or pink, though.
Oh, well. So this one, though, is going to diverge because as you continue your sequence, you get bigger and bigger numbers.
Every time. So don't try and make it converge.
No.
I mean, you're not getting close to anything.
Yeah.
At all.
I mean, if anything, you're getting closer and closer to infinity, which means it diverges.
You diverge.
Here we have -1, +1, -1, +1, and so on.
Mm-hmm.
And so the thing is that just keeps going back and forth between those two.
It oscillates.
It oscillates, which means that it diverges.
Yeah, it's divergent, like those books.
Yeah, it is not at all the same.
Right.
I mean, kind of. They are. Never mind.
Don't they all die at the end? Does that ruin it? Oh, shoot.
Not all of them die.
Okay.
Okay. Example 4, finding limits of sequences. Determine whether the sequence converges or diverges. If it converges, give the limit.
Didn't we just do that?
But now they're doing it. They're
a little different. They're giving us the actual thing. Yeah, okay.
And so this is where if you graph it or you remember your horizontal asymptote rules.
Right.
It's really helpful. Like we had a rule for horizontal asymptotes that if they're the same degree on the top and the bottom, all you have to do is take those coefficients.
I hate to interrupt. This guy's name is EdTech Caveman. That doesn't make any sense.
Would you stop getting distracted?
Sorry.
Okay. If the degree on top and bottom are the same, you just take the coefficients from in front of the
Then that's
variable.
all there is to it. It's just like the horizontal asymptote.
Yeah. So this converges, by the way. Converges to 3.
Right.
And you could graph it and see. No.
Degree is the same on the top and bottom there,
No,
right?
no, this is squared and that's a 3 on the bottom.
Okay, all right.
Okay, so if the degree is bigger on bottom,
goes to 0
it
every
goes
time.
to 0.
Yep.
And so that converges.
3 on the top, 2 on the bottom on the last one.
Okay, so when we did horizontal asymptotes, we said, hey, that's not a horizontal asymptote. That's a slant asymptote.
Hey, divergent.
So that means that it diverges because what's happening is as we head towards infinity,
we're still going
we're going
up.
to continue going up.
Yep. Hey, that wasn't too bad.
No.
So arithmetic sequences, that's a sequence that we can take and write out that has a specific difference of an exact number. So from 2 to 4 to 6, I have a difference of just 2. That would be an arithmetic sequence.
Right, it's a sequence where you add the same thing or subtract the same thing.
Right.
Yeah.
Yep.
Now, you may try to pronounce this as arithmetic whenever you're doing this, but if it is paired with sequence, we typically say arithmetic or something like that.
Arithmetic.
Which is weird. English. Psh. So we call that constant we're adding by the common difference, and we can, anytime we have one of these, we can define it recursively by saying that it's the a n minus 1 plus whatever the common difference is. You'd have to know the first term, like you'd have to have like an a of 1 equals something.
We would need to know.
Something.
Yeah, we got to have a starter.
And then you'd be able to find every other sequence after that. So this has 4 parts on this question, and we're doing number 1. So for 1, part A, we want to find the common difference. So how much are we adding to get to the next term?
Or subtracting. Like what are we doing, either adding or subtracting to go from -6 to -2?
Right.
In this case, it's 4.
Right. So D is 4. And really you need to think of it like what are we adding each time, because if you are really subtracting, you need to put the negative in the common difference.
And one way to find this is take where you're stopping and subtract where you're starting. So -2 minus -6
gives you positive 4.
and it'll tell you exactly what D should be.
Right. So I kind of am frustrated about the order of these numbers because I don't want to have to find the 10th term right now. I would rather write a rule and then use the rules.
Yeah.
So let's write the rules first.
Okay.
So part C, a recursive rule, we would have to say, well, our first term is -6.
Right.
And every term after that we can get by plugging in what we already know, which is a of n minus 1, and we're going to add 4 to whatever it is. That's going to give us our next term. So that's our recursive formula.
There's the recursive rule right there.
D, the explicit rule.
Which is the one that tends to be most handy, but not all the time.
Right. So if we plug in, or like we're changing by 4 each time, so we're gonna have to have like a 4 in, and this is like what the one we did earlier actually. So we're trying to figure out what to put here so that if I plug in 1, I want to get -6.
Right.
Okay, so what am I gonna add here so that when I plug in a 1, I get -6? Well, 4 times 1 is 4. I'd subtract it over and I'd get -10.
Yep.
Okay, so let's try that. If I plug in 1, I get 4 times 1 is 4, minus 10 is -6.
Yep,
so
that looks good.
I just was using that to help me. Now that I know that,
where'd that bug come from?
I don't know. What's my lunch? Now we can go back to B and plug in to find the 10th term. So
yeah, so then now that n then is 10 in this case. So
4 times 10 minus 10.
Right.
So that's 40 minus 10, which is 30.
30, which should work.
Yep.
Yeah.
All right, so on our second one, now this looks a little tricky.
Tricky indeed. I feel like we're going natural log 3, natural log 6, natural log 12.
So what are we adding to each one? So on your grab your calculator, and let's do the natural log of 6 minus the natural log of 3. You might be inclined to say, oh, the common difference is 3, but no, it's probably not. It could be.
I'm on it. Natural log of 6, natural log of 6.
Natural log of 6
minus natural log of 3.
Okay. Now do the natural log of 12 minus the natural log of 6.
Natural
let's see if we get the
log
same
of
thing.
12.
We should get the same thing, otherwise this is very poorly planned on their part.
Natural log of 6. Hey, it gave us the same exact thing.
And let's think about this for just a moment. We did logarithm. Have we done logarithms?
Yeah, we
did logarithms. So you just did natural log of 6 minus natural log of 3 in your calculator.
Wait a second. That's like dividing 6 and 3.
Yeah, you can combine that to this. So what you just got on your calculator should equal natural log of 2.
Whoa! I'm going to punch in natural log of 2.
Okay, let's see.
It's the same thing.
Okay, so even though our numbers are being multiplied by 2, we are actually adding the natural log of 2 each time. So D is natural log of 2. All right, so we'll come back to B a little bit later on. C, our first term is ln of 3.
Yep.
And then every term after that we get by using our previous term
plus natural log 2.
Natural log of 2.
Well, good luck with part D, because I think it's impossible.
Oh, ye of little effort. Okay, so explicit rule. So we are trying to add natural log of 2 each time. So we're going to have perhaps a natural log of 2 times n situation. We want to know, what does this have to be so that our first term, when we plug in 1, equals the natural log of 3. Okay?
So natural log of 3 divided by natural log of 2, I suspect.
Okay, plug it in.
So natural log of 3 divided by natural log of 2 on tray 1.5849. That's what is that?
Well, I was thinking, okay, we just did natural log of 3 over natural log of 2. That's the change of base formula, right? So that's really log base 2 of 3.
What?
Isn't that great? That's a tough problem. So you would have to do
a genius today.
You. Natural log of 2
fuego.
Times n, and if you add that to log base 2 of 3, that is our explicit rule.
Whoa.
Now, using the decimals in both of these cases, like the decimal for ln2 and the decimal down here, I mean, it'd get the job done.
Yeah, but you want to carry through several decimal places because natural log changes and regular log, they change so slowly. You want at least 4 or 5 decimal places while you're working this guy out.
Right, so now let's go back to B and plug in 10. So we want to do natural log of 2 times 10 plus log base 2 of 3. Go for it.
Yeah, but I feel like you're going to like pull some cool trick out and we're going to have like natural log of something. I'll just do it.
I mean, I can get a little closer, but the bases won't match. Like, you could make this be 2 to the 10th, which is, I don't even know.
That's a big number.
It's a big, yeah. 2 to the 6th
log
is 64.
2, 3. I got 8.516.
That sounds like a great answer.
Okay.
8.516. Geometric sequence.
Hey, instead of adding or subtracting, we're going to now multiply.
Right, we're going to multiply by something called the common ratio. And so this time for our recursive formula, it's simply the previous term times whatever the common ratio gives you the next term.
Right.
So we're going to do what we did on the last problem, except for instead of common difference, we're doing common ratio. So here I'm just going to start up here. For number 1, part A.
Hey, you gave yourself more space on this one, so good job there.
Common ratio. So what are we multiplying by each time to get
to the next term? Yeah.
So
2.
2, and then check along. Yep. We're multiplying
You can
by
always
2.
do stop divided by start to figure that out.
Right.
As well.
So 6 divided by 3 gives us 2. That tells us that's the common ratio. Again, I would like to wait until later to plug in the 10th term. Part C, our first term is 3. And every term after that is given by the previous term times
2.
2, yeah. D. So D. An explicit rule for the nth term. So now, when I plug in 1, I get 3.
Right.
And whenever I plug in 2,
I want to get 6.
I want to get 6.
Yeah, so basically what you're going to have is your ratio now being raised to some sort of power.
Okay, so like 3 to the n?
Yeah, let's try that and see what
Not
happens.
3,
no,
2.
not 3, 2.
So 2 to the n, because we're multiplying
2 to the
each
n,
side.
and then maybe times 3.
Okay, so let's see if that works.
You got to start somewhere, right? So if this doesn't work, we'll make a change.
Right, so if I plug in a 1 here, I get 2. 2 times 3 is 6. Well, that's our second term.
Oh, so let's just subtract 1 from n, and maybe that will work.
Up here in our
Yeah,
exponent?
yeah, right there.
So now if I plug a 1 in, I do 1 minus 1, which is 0.
And anything to the 0 power is 1.
And 1 times 3 is 3.
That's 3.
If I try 2, 2 minus 1 is 1, and that gives me the 6 that I want for my second term. So that will be the explicit rule, and it should.
Oh yeah.
That should be something that you can pretty easily do every time. That whatever number you start with times your common ratio to some power. In fact, look, that's right here in our that's almost
there
like
it
a
is.
formula. I wonder if there was one on
Whoa.
the previous slide. Whoops. Okay.
There probably was.
There probably was. So let's plug in 10 into this sequence. So 3 times 2 to the 10 minus 1. You're going to have to help me out with 2 to the 9th power.
2 to the 9th power. That's so big. 512.
Times 3? Times it by 3.
1,536.
I'm so glad we didn't do that by hand. Man, that would have been tough.
Would have been really craptastic.
Now let's try number 2.
Oh, God.
Part A. So what are we multiplying by each time? So it might be more helpful to come over here. If I have 10 to the first power, and then my next term is 10 cubed, which is 1,000, what am I multiplying by to get to the next term?
100?
100, right. Or we could write it as 10 squared if we wanted to. But like Hazelwood said, if we divide these terms, it'll give us our common ratio. So R equals 100. We're going to skip B for now. And then C and D. So our recursive rule, we use the first term is 10.
To the negative 3.
Right. And then every term after that
is 10 to the negative 3 times 10 squared or 100.
Right.
Both of those are the same thing.
So that's
the recursive
C.
part. That's C. So D then is explicit. Look at the top of the page.
Okay, so let's try this time. So A is in this case, is our first term, which is 10 to the negative third.
Yep, 10 to the negative third power.
Times R, which is 100, or you could say 10 squared.
Right.
And it's going to be to the n minus 1.
Yeah.
And then we just need to plug in 10 and get our answer.
Yeah, so, oh, geez, that's yet another big number. I'll just start typing it. That's a bunch of zeros.
10 to the 15th.
How did you get that? That's what my calculator said. Look at that. How'd you do that? Did you do that in your head? That's the right answer.
Is it though? Because yours is in scientific notation.
It's 1 times 10 to the 15th.
Oh, you're right. You're totally right. Okay. I just used exponent rules. So 100 to the 9th is the same as 10 to the 9th squared, which is 10 to the 18th.
Yeah,
and then
you smart.
All right, so over here I have from your notes, this is on the arithmetic sequence. This right here would be, which we didn't point out, this is a formula that you could use to always write the explicit formula for an arithmetic sequence. We did point out for the geometric sequence that, hey, this will always be something that you can use, and in either of these cases, a is our first term, and so we're going to use that on this problem now for constructing sequences. They tell us the second and fifth terms of a sequence are 3 and 24 respectively. They want us to find an explicit and a recursive formula for both of these cases. So a is going to be arithmetic. Now the tricky thing with this is they didn't tell us the first term, they told us the second term, they didn't tell us the third or fourth, but they did tell us the fifth. So for arithmetic, I'm going to start off by saying, well, I know it has to follow this general rule that the nth term is the first term plus n minus 1 times d. But I don't actually know any of those letters right now, like any of my variables. I do, however, know what that I have a2, right? I have the second term, so it equals the first term plus 2 minus 1 times d. And actually we can say a2 is 3. The second term is 3, so that equals a1. 2 minus 1 is 1, so that's just a1 plus d. Then I can do this again, thinking about the fifth term, that a5 equals our first term plus n minus 1, so 5 minus 1 times d. The fifth term is actually 24. We still don't know the first term, but then we can do 5 minus 1 is 4d. Now we have a system of equations that we can solve, which may seem a little weird to you. Excuse me. But I'm going to multiply this equation by -1 so that I can eliminate my a's. So -3 equals -a1 minus d. So that's 21 equals 3d. Divide by 3. And you get d equals 7. So that's the common difference, and I can plug back in, like over here, to get a1, because 3 equals a1 plus 7, so subtract 7 over, and you get a1 equals -4. So both of these things now help me write the explicit formula, so that's a of n equals -4 plus n minus 1 times d, which is 7. Okay, that's just taken straight from this right here. The recursive formula, we need to know what a1 is. It's -4. Then every element after that comes from a of n minus 1 plus our common difference, which is 7. So the first one is explicit, the second one is recursive. Now let's do it for a geometric sequence. So this time I know that an equals a1 times r to the n minus 1. So they told me what the second term was. So I would plug in 2 minus 1. Well, that's going to give me 1. A of 2 is 3. So this is 1, so r to the first means that I just have a1 times r. Now I would do it with a5. Okay, so this is supposed to be 5 minus 1. And a of 5 is 24 equals a of 1 r to the 4th. If we solve this for solve this for a1, then we get 3 over r. We're going to plug that in over here. So r to the 4th over r gives us r cubed. So that means we have 24 equals 3r cubed. Divide both sides by 3. 8 equals r cubed. Cube root both sides tells us r equals 2. So then we just have to go back and plug in, for example, over here. If I put a 2 right here where this r is, that means a of 1 equals 3 over 2. So 3/2 is a1. And now I can write our two formulas. A of n equals our first term, which is 3/2, times 2 to the n minus 1. And then recursively, a1 is 3/2. An equals our term in front of that times 2. Timesing by 2 every single time. So there you have it. This video brought to you by KitKat.
And Big Gulp.
Here's the code word, KitKat and Big Gulp.
Or just KitKat.
Whichever,
Solar.
just one of those, something like that. Okay, so example 8, graphing a sequence defined explicitly. It's actually a really cool thing to see on your calculator. So, bam, calculator appears as if from nowhere on the screen, right? Right?
Done. Consider it done.
Okay, so all you do is there's a mode on your calculator. It's like it has function mode, polar.
Sequence.
It's SEQ for sequence. You pick that, and then when you go to y equals that button, now all of a sudden we have like u of n.
Which you can see right now.
Right, and so it gives you like, you're going to type in, you're going to type in n squared minus 1. The n is the variable button. That
right.
button that you use for x will turn into whatever variable you need.
Depending on which mode you're in. So in this case, we're in the sequence mode.
Right, and then you're supposed to put in for, and I'm sure it's showing up on the screen, but what is it? It gives you...
Sorry, my alarm's going off.
It has u, and then it says n min, and you're going to put in 0 for that. And there may be some other things, but you can see it right now. It's showing up on your calculator. And when you graph, it's just gonna show you those like
the dots.
Yeah. So that's pretty cool. It's a pretty neat thing. Last example, also a calculator cool thing, which I went ahead and put screenshots on here for you. If you wanted to basically program your calculator to help you get terms of a sequence.
Shut the door. You can program these puppies?
Yeah, you can. So if you're given an explicit formula like this, we would start off with 0 for k.
That's storing 0 as k.
Okay, and so then that's basically you're gonna start at 0, but then we're plugging in k plus 1. This arrow button is
that stores it as the new k.
And to get that arrow.
It's the stow button.
Yeah, which is gangster for store. It's over on the bottom left of your calculator.
Yeah.
So
Did you say gangster for store?
Yeah, you're gonna
stow it, man.
You're gonna stow it, yeah.
G.
So you're gonna stow it, and then it's saying this is our formula up here, 3k minus 5. And when you do that, what it does is it adds 1 to k, so it makes k be 1, and then.
And then it does 1 times 3 minus 5.
Right, so this is the first term of our sequence, right? If you plug in 1, you get -2. And then if you keep pressing enter, it will give you consecutive terms.
Craptastic, that's fantastic.
Then if you wanted to do a recursive formula, this is the same thing twice. I wonder what happened to my other screenshot. I had a different screenshot here.
That's not the recursive formula, as it turns out.
That's not the recursive formula. So instead what you would do is, it's actually really simple. All you have to do is you start with, when I plug in, we start with -2. So you type in -2 and you press enter. And then you just basically, you don't even have to store it for this. You're just adding 3 each time. So you put answer plus 3 and then press enter and it gives you 1. And then you just keep pressing enter and it keeps giving you.
You don't even have to do anything.
You don't even have to
That's
store
right,
it
because the calculator just automatically does the next thing. Yes.
So that's kind of, those last two things are just kind of a neat, here's something you can do kind of thing.
There you go, that's fun.